Now we can go a little bit further. So rather than looking at Coulomb's force, Coulomb force from the P401 viewpoint. And I'm going to go ahead and pull up my equation sheet and do some cutting and pasting here to see how it's different. And part of the reason I'm cutting and pasting, as you guys are going to see, is to make sure I'm getting my symbols correctly. So I'm going to come over here to my notes and I'm going to pull up these equations. And these were equations that I pulled out of the textbook. And we will pull them from the textbook or look at them in the context of the textbook here in just a minute. But I'm going to go ahead and grab this and put this into my document. And then grab another equation here, actually a set of equations. Okay, so I've got those cut and pasted. And what I'm also going to do here is, I should probably put a link to it, but we're going to go into the general resources and I'm going to open up the electronic version of this textbook so we can see where some of this stuff came from. So on page 60 of your textbook, in section 2.1 is that 2 or 1? 2. We have this one, which is equation 2.1 in the textbook. Okay, so this is where it comes from, and it's going to go through, and it's a little bit different than the way I presented it in 255. So let's talk about those differences. First of all, rather than using Coulomb's constant, it uses our epsilon naught permittivity of free space. But we saw back in our general physics that K is actually equal to 1 over 4 pi epsilon naught. We didn't introduce epsilon naught until later on when we were starting to do Gauss's law. But we have these two relationships. So while K is equal to the 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, epsilon naught is equal to 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. So these two constants really refer to the same physical number. If you were to take 1 over 4 pi and this number, you should get 8.99 times 10 to the 9th. Coulomb figured this out experimentally. Epsilon naught, the permittivity of free space, is actually related to the speed of light in a vacuum. And so that's why we have this permittivity of free space. It's how well does the electric field, how is it permitted anyway, it's awkward. Our textbook author calls it a ludicrous name. I don't think it's a ludicrous name, but it's a little harder to understand. And I always misspell it, which is why I let you guys just call it epsilon naught. it is fundamentally more closely related to what's going on, and so this course uses that. But if you're solving a problem that has 1 over 4 pi epsilon naught, and you want to just plug in 8.99 times 10 to the 9th, you're free to do that. We're just simplifying it a little bit. You can use either one when you plug it into the problem. There will be times where when we're doing something symbolically, leaving it as 1 over the 4 pi epsilon naught, either something with the 4 pi or something with the epsilon naught may cancel out. And therefore, leaving it in that form allows us to work with it symbolically a little bit easier. Okay, other differences between these two equations. It uses little q and big Q instead of Q1 and Q2. So when we were doing this, it doesn't really matter which one you're calling which one in terms of Q1 and Q2, because Q1 and Q2 were just sort of placeholders anyway. When I actually did an example problem, it might have been QA, QB, and QC. The reason they use a little q and a big Q is because they move very quickly from Coulomb's law for the force into the electric field. So they're using this one as a test charge at some point in space. When I get to some other things, this is the field point. And this is our source charge at a specific location in space. Taking it back to my previous example in our other video, if we have a QA, a QB, and a QC, and we're finding the net force on charge A, then Q, capital Q, is my QA. And my little q is equal to first QB, then QC, because I have to do it with both of the other charges. So does that make sense?
Repeat that last part.
For my previous example, the little q is first it's going to be QB, because I'm finding it on QA due to QB. And then it's going to be QC because I had to separately apply the equation for each pair of charges. So if I'm looking for it on QA, this is my test charge where I'm trying to find the field. Now, let me bring back up the textbook here so we can see a picture of what they're looking at. They've got some field point out here, P, and they've got a bunch of different little charges. And they want to find the electric field at this point due to each one of the other little charges. So this is like my test charge, and these are my source charges. And so I've got a bunch of little Q's that are all going to be different, but I've got one point in space where I'm working with it. Okay? So when they go through and look at that, I want to find that Q, big Q out here at this place. If I were to put a charge there, what force would it feel due to all these other charges? Okay? So they go ahead and make that. So when we go through here, when we look at all of this, and we'll look a little bit more at this in one of our future lectures, they immediately say, I've got several different charges away from one charge. My one charge is the charge I care about, my test charge. And so since all of those have the same capital Q, they start doing some other stuff with it. We'll get to this. But just for now, showing you that difference between if I have individual charges, one of them is a little q and one of them is a big Q. Yes?
What's below the lower case Q and the uppercase Q? That's an H squared?
So that's our next difference. Very good question. Okay, so we've talked about the difference between K and epsilon naught. We've talked about the difference between Q1, Q2, and our little q, big Q. So now we talk about what's going on there. This is a script R. Okay? So in this equation, this R script, so it's kind of a cursive R, is our separation distance. That's how we used little r previously. But when we're doing it at this level, we want to specify positions of each vector. So R is a vector for the position of our field point, and R prime is the position of the source charge. And so R as a vector here, when it's in bold, that's the full vector separation. This is the magnitude of the separation, so it's just a distance. And this, with the hat on it, is the direction for that separation vector. So, next class, we're going to dive into these equations for the separation vectors and handle this as full 3D vectors and how we can do that with our full vector notation as opposed to what we had to do in our previous stuff. Now, if they just give you the separation, you just use your separation as your R. So this script cursive R, which I'm not very good at drawing cursive letters. I really suck at writing cursive letters because it looks like a mu or it looks like an H or what the heck is it? I have a very hard time writing that handwritten. What I end up doing most of the time is this is sort of my best handwritten for me. So when I'm doing that, that's the separation vector. Feel free in class to ask me to clarify if you can't tell what I've written. Okay? So this is the way it's written in the textbook as a cursive R, a script R, as the separation distance and the separation unit vector. So that's where I'm going to stop for this video, just going through and talking about this equation and where things came from. Now, I will also mention that this vector stuff in here, which we'll cover more next time, came from chapter 1. So in our textbook, when we come back here to the vector analysis and our vector algebra, the vector position, displacement, and separation vectors are part of what was in that section. And so if you want to go back and look at that before our next class, that is in section 1.1.4. Okay?